Good morning. So it's kind of very hard to follow what after John's talk or Mandar's talk, but I will try. But good thing is I hope I don't have to talk a lot. I would like to do something here. In the morning when I came in, I was like a bit happy because there was only like 3 or 4 people, but now I see that there's a lot more people. So more pressure on me. Anyway, super glad to see all of you here. I think in 2013 when we started, probably half the people, they end their competition. So, and I've been very, very happy to see it come all this way. Before even I get into anything, because I know like what John was saying, it's the morning after, night before. I don't want all of you to fall asleep. So I hope I can wake you up with this. I can briefly explain what I did. So I have 2 laptops here, one here which is not connected to the HDMI, so you can't see what I did there. But in my laptop, I am running, or both the laptops, I'm running a software called UnetAudio, which is something I will build on through the talk. But basically, I transmitted something. You heard some sound, I believe, it was a bit annoying sound, and you can see that there is something printed there. So I'm going to do the same thing now. But this time, not from a laptop. In my phone, I have the same sound recorded. Hopefully it works. Let's see. There you go. So again, so I will try and build to how you can all do this. As much as possible, I will try to avoid going into the details of how we build the system, but how you can build the system, okay? Now, going back to my talk. So what I did do is just this. So I have 2 laptops right next to each other, and I also had a phone recording. And all I did was I have a command shell where I type the command tell 0 hello SAUVC. I will show you typing other things and doing that in a bit. Now that that's out of the way, I would like to thank Rajat for giving the intro. So I would like to start, like he was saying, by why we are doing this, right? Because he was saying that we should always ask why are we doing the things that we are doing. And then I will go on to how can we do this and hopefully show you how to build it. Okay? Now, while I did this from one laptop to other laptop using sound, and I thought that will wake some of you up, we can do the same thing with light or electromagnetics. As in most of the terrestrial communication we use electromagnetics, so it will be not fair to those technologies if I can't do the same, right? So why are we doing this? Before, again, getting into the details of why are we doing this, let me give you a bit of a background about me. Like Rajat was saying, in the last, maybe this is the 9th year since we started SAUVC. First year was in 2013. And almost all the years I had the privilege of doing the photos and videos. So that gets me intimately close to many of the teams to see all the robots and technologies that you guys build and bring to Singapore. And I've always been very, very inspired about the kind of things that you do, right? And in fact, what I'm trying to do today is partially inspired by all of you. So thanks to you. And when I'm not doing photo and video, I work at Subnero, like what Rajat was saying, where we try to bring wireless and wireless technologies and internet underwater. But that was not always the case. The very first time I was exposed to wireless technologies was during my high school days. So I was interested in building hobby circuits like many of you. And I used to routinely go to my electronics store at my town and then buy hobby circuits, hobby kits. I didn't understand anything about it, but they would have detailed instructions. I just get a soldering iron, solder it, and then press some buttons, it'll light a light or make some sound. But I thought, okay, I saw in some of the science fair that people are actually building FM radio where you can transmit like a walkie-talkie and someone else can listen. So I went and bought a kit. And I tried to, I followed the instruction exactly the same way. I tried to build a radio, but no matter what I do, it doesn't work. Whereas the rest of the things I do the following, follow the instructions, it will work. So I figured out, I tried troubleshooting for a very, very long time, and eventually I found someone who was a senior who had done the same, and he explained to me that, oh, your coil winding is not right. So I had to do some coil windings at that time, and I had no idea why you have to do that, and we made it work. So at that time, it felt like a bit of a black magic to me, because you have two systems not connected by wire, there is nothing you see, but you do something here, it just magically appears on that side. So that kind of fascinated me. Fast forward 6 years or 7 years, I was working at a company that does Wi-Fi routers, and I was a software engineer doing the firmware. And I still remember the first time I coded some signals and transmitted, and using a third-party device, it captured and printed it out. So I was super excited to see actually I could transmit something that is completely invisible, nobody can sense it, but it can still be received on the other side. So with all of this excitement, I decided after some initial years of working, like a couple of years, I decided to do my master's. So I had to figure out, what's happening in the wireless world, and I really wanted to see how we can push some of these technologies to get better performance. And I came to Singapore to do my master's. It was National University of Singapore. And that's where I met Dr. Mandar Chitra. So I was his graduate student. I was taking his class, and I was very much interested in what he was teaching. And I asked him one day that, hey, I like wireless networks. I would like to, build a career in wireless networks. What do you suggest? Then his answer was like really, really interesting. He said, terrestrial wireless is easy. I'm like, that doesn't make any sense, because it was so hard for me. What he was trying to tell me was, doing terrestrial wireless is relatively easy as compared to underwater wireless, right? Underwater wireless is challenging and has not very good reputation because it's so hard. And he's like, if you want a challenge in life, try building underwater networks. Not just point-to-point wireless links, but networks. And I'm like, okay, let me see. But the question was, for me, was not about building the part. Who needs underwater networks? Because I have no idea why do even people go underwater, right? So I used to dive. I still dive a lot. So the only people I can think of are divers. But we use hand signals to communicate underwater. We don't need anything more than that. And then I did join ARL as a graduate student or research engineer, and where I worked, and I met all of these amazing people here. And over the years, I believe it's almost like 15 years now, or 13 years now, I have a very newfound respect for this domain, because the kind of challenges or the scale of the challenges that we face underwater is drastically different. I would say a lot more challenging, partly because most people don't know about this, in the case of, as compared to the terrestrial wireless networks. I had to wait for, even after I started my career, I had to wait for 4 or 5 years before even I heard about underwater technologies, not even like communication or robotics, right? And that's really the reason why SAUVC was formed. So the picture that you see there is from one of the very first committee meetings in 2013, and you can see most of the people are still the same. So this is the same questions that we were asking at that time. Not me, I was a volunteer diver at that time, the core committee. How can we expose this world of marine technology and marine robotics to more and more students like this? So that's why I said I'm very happy to see so many people here, because, and then if you look at the website, this is what you will see there. It's actually written there. These tasks are simulations of tasks operational AUVs have to take in real world. So again, going back to why we are doing this, always the idea was, okay, we can set up a lot of challenges, competitions, get people interesting, but it has to have a goal to show what are the real challenges that we as marine technologists face in a day-to-day life, like what John was showing, the ocean, the video that he was showing. You can hear it, you can listen to it, you can see videos, but when you actually are out there, I still remember one of the days, like a couple of years back, we were out testing something, and I couldn't do anything. I was just on the floor of the boat, just lying down because the boat was rolling up and down. I couldn't even look at my screen, and it was like, I know some of the people here knows this. So when you actually sit here in a nice place and then see it, and then going out is a very, very different experience. So that's what we wanted to give a bit of a feel for. So we can organize a lot of events or talk about it, but we thought, or the original committee thought, let's go have a competition where people come and dip their toes or like the entirety of their body in water and get build robots and do tasks. And the tasks are actually modeled after some of the real world challenges that we face in the sea when you go out, right? So if you look at these two pictures, the first picture on the left shows the picture from 2013. This was one of the tasks at that year, where so it was primarily focused on navigation and visual sensing. So AUV had to follow, so you can see there is a white color thing, the AUV had to follow that black mark, mostly visually, and pass through a gate. But fast forward to 2022, this year, you know, there is no white color mark. It's the same pool, by the way. There is green area where you have buckets, and there are some flares in the starting area and all of that. So the tasks have evolved in complexity, but again, to represent or closely mimic what actually happens in the real world out there in the sea. So now you have to ask the question, now we are almost at 10 years. Where do we go from here, right? So if you look at who are the people who actually use underwater technologies, robotics or communication, the same question that I was asking 12 years or 15 years back, there are 2 or 3 major segments. So obviously there is a defense segment who use it for applications like surveillance and mine countermeasures. These are typically tend to be longer torpedo-shaped AUVs, which can cover large areas, but for a set of survey kind of applications. Then there is a commercial sector, which primarily uses ROVs because they need a lot more degrees of freedom and not just inspection, they need intervention because they will have manipulated, they will have to turn knobs or pick up something. So that, as compared to AUVs, the area of operation is typically smaller, but they need to do much complicated tasks. And then there is the scientific research domain where we try to push the envelope of what is possible. So there are all kinds of vehicles there. There are so there are the torpedo-shaped AUVs as well as the ROV kind of vehicles or even hybrid vehicles, which is where SAUVC is, right? If you look at all the tasks, you still need to do tasks that are complicated, need high maneuverability. You need intervention because you need to pick up the ball, which I don't think anyone had, not many people have attempted this time. But that's really where we want to go without a tether. That means you are focusing a lot more on autonomy. It's completely autonomous. There is no human in the loop in the middle, right? But if you look at real world scenario again, that's kind of limiting in a way because it's not because of the lack of communications, wireless communication system in the case of underwater that nobody uses it. It's just the niche is slightly different from what we are accustomed to on land. On land, we have long range, high bandwidth systems. But when you go underwater, usually you have high bandwidth systems which are very short range, optical or RF. But because electromagnetic gets absorbed rapidly in water, when you go long range, you use acoustics, which means it's very, very low on bandwidth. So you have to work with your vehicles with either this very, very short low bandwidth systems to make it work. But if you look at, while it's not as prevalent, we all believe that it's the future, that where we are going towards, and in fact there are many companies that I wouldn't claim it as sold, but they are actually building vehicles that are moving not completely on the autonomous side or completely on the remote control side, but somewhere in the middle where you are going towards supervised autonomous systems. So these systems, so in the case of autonomy, some of you, I believe most of you might be familiar. So when you try to do the tasks, first task, it's really good, right? So because it's very short task and you go there and then you can program your vehicle to do one task. But when you, so you can program to do your vehicle to maybe just find the flare or the other one. But when you try to connect them, all of them back to back, it becomes a bit more complicated because it's not easy because the vehicle will have to make decisions on the fly right then and there, which is kind of hard. But if you have a human in the loop where you have a very low bandwidth system where the vehicle performs autonomy in smaller chunks and then humans can control it or give some commands to reorient, that can provide or potentially attain much better results. So coming back to my question, of why do we need to do this and why am I trying to show some of this. Obviously, it's fun for me and interesting, but in the future iterations of SAUVC, there will be tasks where you can potentially use supervised autonomy by using some kind of remote control systems to talk to your vehicle to perform some task. I don't have the details of the task yet. That would be to the decision of the technical committee, but that's why we thought, okay, doing a workshop now would be relevant to show how to build a very low-cost DIY modem. So if you look at, I briefly mentioned earlier, if you look at the commercial systems out there for underwater wireless systems, there are two main classes of systems. One is acoustic, typically used for medium range to very long range communication, but low bandwidth. Or the optical systems, which are very, very short range, but high bandwidth. You can see that light actually gets absorbed very fast in water, especially the waters are murky, tends to be, different areas can be very clear, some areas can be very murky. So depending on that, the range varies. And then there are some systems that are RF for the completion of it. I'm just telling it, but they're usually used by submarine, very low frequency, but for this purpose of this discussion, I will probably don't go into the details of that. So if you look at a basic building blocks of wireless communication system, you take any textbooks or any digital communication textbook, you will see some variation of this, right? So you have some information that you want to transfer from one point to the other point. What you do is you take that information, you convert that into some kind of representation that you can transmit. So in the case of digital communication, you will translate to a series of bits and bytes, ones and zeros. And then you do something called channel coding and modulation. So you have these bits and bytes, but you need to represent that using some kind of physical phenomena which we can transmit, like sound or light or electromagnetics. And then what you do is you convert that to the actual physical phenomena. In case if you're transmitting with sound, then you use a transducer or a speaker, and then, or if it's a optical system, you use LED. And then on the other side, you use a receiver. In the case of sound, mic or something similar, like in the case of underwater, you use a hydrophone. And you do the reverse on that side, and you will retrieve the data. In the case of acoustics, while in the case of electromagnetics, that's something that you have to learn. But in the case of acoustic communication, if you really think about it, this is something that we do every single day, right? So if I am talking to someone, let's say Amy, I have to transfer some information which I will think, and then I convert that to some kind of representation using words, and I use my vocal cords to modulate the sound, and I talk. And there is no wire between me and Amy. On the other side, she uses her ears and listen to that, and which converts the sound to some kind of electrical signals, which goes to the brain. It's the brain decodes, and that's exactly what acoustic communication is doing. A simple acoustic system, without going into a lot more detail, is whatever I just explained. Instead of using words, in the case of a digital communication system, I will translate that to ones and zeros. And that ones and zeros will get translated to a frequency. So let's say I can use two frequencies to represent 0 and 1. So if there is a 0, I transmit one frequency. If there is 1, I transmit the other frequency. And that's what we call FSK, or frequency shift key, and that's about it. And in fact, if you remember the sound that you heard, that's basically what I'm doing, right? I have different tones which represents different pairs of ones and zeros, and that's why if you listen next time when I play it, if you listen, you can hear that it is ting, 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 something like a piano, and that's what the communication system is. Now I want to bring one more concept before we going into actually building or showing some of this. It's a concept of software-defined modem. So some of you might be familiar with this. Another way in which it's very famous is called software-defined radio. So if you look at the Wikipedia page, it says that a software-defined modem, or a soft modem, uses software to do a lot of the computation which are traditionally done by hardware. So if you look at any radio, a piece of equipment that you take, it has like a traditional radio, it doesn't have any software in it. All of the radio is built or implemented with actual hardware and filters like transistors or coils and the things that I couldn't get it to work 15 years back or 20 years back. But in the case of software, with all of these computing powers that we have, I can do all the things that I just said, like from taking the information, coding all the way to the passband signal or the equivalent representation of sound in the digital domain in software. Then all I have to do is just translate that information, which is usually stored in some kind of electrical voltage, to amplify that and then transmit that to sound or light. And that's all I have to do. So with all of this computing power that we have, it should be much, much easier to build a acoustic or a wireless system that we can use underwater, either acoustics or wireless or any of the other channels. So when it comes to a software-defined modem, the block that I was showing earlier will become like this. So I will do the source coding, channel coding, and modulation, all of that in software. All I do is I use a digital to analog converter to convert that voltages, signal, the digital representation to some kind of voltage, and then I transmit it through sound or some kind of wireless phenomena. Now, one very common, very famous example, some of you may have already seen or used this even in the past, is GNU Radio, the one on the left. And that is just that you can actually download GNU Radio to your laptop or even a Raspberry Pi. One of the example is from that Spectrum article. That's a Raspberry Pi, and all you have to do is just run that software. You can have your own, create your own signals, or transmit or decode, encode your own information, and then transmit it out using, in that one they are using a TV tuner to do a RF. But in the case of underwater, there are some of the software, but if you try and take GNU Radio and try to do an underwater network, what happens is if you're using RF, yes, it probably will work straight out of the way. But then if you want to use anything meaningful, you want some range. Even in the pool, RF probably won't work more than a couple of meters. But if you want to communicate to your vehicle to do something or tell it to do something, you might want something that propagates light slightly longer, either light or sound. So in the case of sound, there are some basic fundamental characteristics that are different from light. To begin with, sound travels 200,000 times slower than light, right? So if you use a software that is designed for electromagnetics and use it for acoustics, then many things break down because the fundamental assumptions are wrong. So I will be using a software called UnetStack. I will go into the details in the next slide, I think. This is a software that is built very specific for underwater networks. We started with that, but now you can actually use it for any type of physical layer. Let me walk through that how. So if you look at UnetStack's website, unetstack.net, you can see that it's a collection of technologies, not just one stack, while it started as a stack, and that's the stack in the whole name. It is a collection of technologies to extend networks underwater, right? So earlier in the talk, John was mentioning that, yeah, you can send sail drones to wherever, and I can be at my office, look at whatever it is they're doing happily. But what about AUVs? I also want to do the same thing with AUVs, right? So AUVs or any kinds of vehicles, so they can also send these kind of information, maybe images, depending on the speed of your link, maybe some sensor data to a surface, and you can have a gateway buoy that converts from sound to RF and then send it back through Iridium or any kinds of similar technologies, Wi-Fi or GSM, back to your office so that you have the full end-to-end connectivity completely transparent. Currently, if you look at the website, you can see that it is UnetStack 3. That's the one that is out there. In fact, because of some of the things that I mentioned, we really want to make it available for the research community. Okay, maybe before that, a bit of a background about UnetStack. So UnetStack is completely developed in the lab that I worked. I was one of the research engineers. So earlier I mentioned that I joined ARL as a research engineer. So I worked on the original technology, some of it, and a lot of the code is written by my colleagues here, Mandar and Chinmay and a bunch of them. Because of our research background, while we do a lot of commercial stuff, we want to make sure this technology is available freely for people from research or enthusiast backgrounds to download and use it. Because when we tried to do something like that 10 years or 15 years or even before, there was nothing similar available. So we do have an edition called the Community Edition, which is free to download and use for non-commercial applications. So more than welcome to download and use it. So back to where I was. Currently the version is UnetStack 3, which you can see we have a lot of blobs, which again I will go into some of the details later. But UnetStack 4 will be released shortly, which has a lot more features and capabilities. You can see that all of the smaller bubbles are into bigger bubbles there, so a lot more features. That's basically this slide is about. And before we try and go and build some of these, I will walk through some of the resources. So first and foremost, the single stop that you might want to check is the unetstack.net. And from there is a unit handbook. Again, this session is not about underwater, how to go into the details of the underwater. It's just like use the software to build something and transmit between two entities. But if you are interested in learning more about it, by all means, unit handbook it's basically a textbook that explains about underwater networks and various challenges, including some simulations of our deployments in and around Singapore. We do have some video tutorials for those who don't like reading. Go watch it. We do have blogs. In fact, this particular session that I'm showcasing actually are based on two blogs that we have published in the past. One is how to convert your laptop into a modem, and the other one is how to build a very low-cost DIY acoustic modem, which is what I have set up here, also in a blog. Then we have the Unet Contrib GitHub repo. The idea is that if the community, we do have a lot of people in the community who use UnetStack. They sometimes say that, oh, I would like to build something and I would like to contribute back to the community. I would like to push it to our GitHub repo. So we have a contrib repo. If any of you are interested, by all means, we'll be more than happy to get inputs from the community. And then we also have the support forums. We try to support as many users as possible, as fast as possible. When you try all of this, if you face any problems, do post there. We will try and respond to as fast as possible. So just before going to the next one, I wanted to show you. So this is the UnetStack website. This is what you will see. And this is Underwater Network Handbook. You can see it's very detailed. These are the video tutorials, the blog, and the support forums. Okay? Okay. Now, enough talk. Maybe I will try how to build. Feel free to build and go along with me. I have some colleagues who can help you if any of you feel some issues. So all you need is a laptop with either a Linux or a Mac. You need Java 8 runtime. You need a driver called Port Audio. And the instructions on how to install those on Mac OS as well as on laptop is on the right. If you're interested, go try it out. If not, by all means, no. And then you need a browser. Any modern browser will do. Chrome, Safari, Firefox. And then you just need to head over to unetstack.net, download so I can show you where to download it from. So if you go to unetstack.net, and if you click downloads, go to download, you can just say accept, and you will be able to download it. And that's all you will need to do. There's nothing additional you need to do. So I'll give maybe like 5 minutes for if any of you want to try out before I go and show the rest of the things I want to show. So once you download the zip, you unzip it, you open a terminal. Just make sure you have all the prerequisites ready. It has to be Java 8 or else it won't work. So it probably will be fixed in the next version. Once you have that, you open a terminal and then type that. So there is a binary folder, so bin/unet space audio and press enter. And when you open that, it will open a web interface, which I will show you in a second. And then you can transmit something straight away by just typing tel 0. 0 is to broadcast. So if there is a specific address that you want to transmit, you can just use an address like an IP address, comma, comma, whatever you want to transmit. And then if you have two laptops right next to each other, and if both of you got it working, you can transmit and receive on the other side and send and receive using that. Okay? So here it goes. So tel 0. Oh, sorry. Hello. And if I do this, then I believe you can see that. So that's all that is, right? So using a speaker and a mic on a laptop to transmit is one thing. But if all of you want to put an acoustic modem or an optical modem or any kind of modem in your vehicle, I don't think any of you would like to put a laptop inside your vehicles. Yeah, now I think it's not you. So, yes. So what we want to do is, it's just a piece of software that all of you downloaded. Why do I have to download and run it in my laptop? Why can't I just download it and run it in a Raspberry Pi or any of the standard SBCs, which is what I've been trying to set up, right? So this is the second blog that I was saying. If you go to blog.unetstack.net, the top one right now is about this. How can you build a DIY modem, which is less than $300 with commonly available components? Now, let me just walk through the components there, and then I actually have this whole setup here on the table. I will do a small transmission and reception, and later after this we can try more complicated stuff, and I will show you what happens, right? So, like I was saying earlier, what we need to do this is a laptop, and to do the conversion of the signals to electrical signals, you need so usually you need a digital to analog converter, but in the case of a laptop or a single board computer, what you need is a sound card. And I have bought a USB sound card, which is like $2 or something from AliExpress. And you connect it to your Raspberry Pi, you download the software, you run it. Then all you need is some way to transmit and some way to receive. Now, I can straight away show using a speaker that works on land. But what we are interested in is doing this underwater, right? So all we need is to take a speaker and a mic and waterproof it. So if you go to eBay and look for underwater speakers, you can find this. These are just speakers somebody has made waterproof, which you can put it in pools. People use it to play music or do PA announcements. So this can, again, I'm not saying to put this in your vehicles. You can if you want to. But traditionally, if you look at any acoustic modem companies, oh, I want to buy a modem, those typically start at least $5,000 US. And that's beyond the reach of many of us here. And that's actually what we do. So if any of you want to buy a modem, just let me know. I'll be more than happy. But if you look at literature, it's not that people have not want to buy or build a low-cost acoustic modem. Wow. Low-cost acoustic modem. But most of the low-cost acoustic modem, in fact, some of them I have listed in my blog. In fact, I think I have someone, or maybe, listed in the blog like Ahoy modem, C-Track modem, and one bunch of them. But most of them need custom hardware. So for me, personally, custom hardware means more time. And many of you, it might mean more expenses. And you need to know how to build it or do it. So that's why we don't want to have any custom hardware. Everything commercial off-the-shelf systems, we download the software and run it. And on the other side, what you want is just a mic. So you can buy hydrophones and connect directly to a sound card on Raspberry Pi, no issues. But I don't even want to buy hydrophones. Even the cheapest of the cheapest hydrophones are hundreds of dollars. What we want to do is very, very, very minimalistic, very cheap stuff. So I have it there, which I can show you in a second. Basically what you buy is just buy normal standard condenser mics or electric mics, put in a lot of hot glue, and then just connect it directly to the sound card. And it works for the kind of applications that we want to do in a pool. And in fact, that's what the mic is. So in the blog, I have actually written on how we have made it. Feel free to experiment, and then if you have better ways to make it, please do let us know. We'll be more than happy to publish it for you. So I have, to summarize, we have a transmitter Raspberry Pi, receiver Raspberry Pi, 2 sound cards. On the transmit side, I have an underwater speaker, but to drive that, I need a power amplifier. It's just a $5 power amplifier that, again, I bought from AliExpress. And that underwater speaker, I believe, can take up to 30 watts. So you can build your own if you want more power. And then the underwater mic to receive it, right? So translating the blocks that I showed you earlier to this particular build. So I have a Raspberry Pi, USB, audio amplifier, underwater speaker, and on the other side, microphone. I don't have any amplifiers because it was doing more than good enough. USB adapter and Raspberry Pi, right? And like I said, all the details are in the blog. So let's see whether it works. So I have both of that here on the just down in front of the table. I want to actually do it on air first. I have a bucket of water. We can try it out later. I don't want to put it in water so that water spills. But let me show you how that's going to work. So earlier I talked about I have 2 Raspberry Pis in my table. So what I have on the screen is I have connected to the transmitting Raspberry Pi on the left, receiving Raspberry Pi on the right. And you can see that there are 2 things that I set. So again, without going into a lot more details, what I'm trying is when you use your laptop, you download the system when you're transmitting, it is using a speaker band. So it's from 9 kilohertz to 15 kilohertz. That's why it's a high pitch sound. But the underwater speaker that I'm using do not respond in that high frequency sound. It is actually slightly lower frequency band. So I have to set the starting frequency to 4.7 kilohertz. And if you listen to this sound, like I was saying, what the scheme is called is a frequency hopping BFSK. So 1 tone for 0 and 1 tone for 1. And then it keeps switching. And that's why you hear this kind of sound. Now, how many steps or what are the different frequencies are determined by the parameter called step. Again, you probably don't have to do any of this. I'm just explaining to you so that you get a feel of it. All the details are on the blog. You can take a look at it. So what I did is I am running the software in Raspberry Pi. And I changed the 2 parameters. And I am just going to transmit this. And you can see that it's coming from there. Yeah. And you can also see that it's much longer now because I have reduced the frequency. So I'll transmit one more time. And you can hear it. And you can also, so this one I believe because there was a block, you can actually see that the first transmission got picked up by the electric mic on the other side and it actually printed. We can try that one more time. I don't know. Sorry. You can see that. So it's basically is transmitting from one Raspberry Pi going through the power amplifier, underwater speaker, on the other side it's a mic, directly to the Raspberry Pi and it's decoding. So it's as simple as that. All you have to do is just download the software. You don't even have to buy a Raspberry Pi. Most of you have some kind of single board computers in your systems. All you need is a power amplifier because you need to drive a speaker. And if, for those who have enough money, you can buy a slightly better hydrophone because this is big and bulky and all. But the whole point is to show that this is as easy. Whole complexity is in the software. Okay. Now, I want to actually do some more cool stuff before I end the presentation. I don't have a lot of time. So what we did was we took some information we transmitted, and you have no control on what actually transmitted. But there might be some places where you want to transmit your own sound. So what if I type that? So if I want, so maybe for people who have this working in your laptop, try typing that, BBTX space CW in bracket 8000, 1. Does anyone want to try that, or shall I show you? Yeah, I hear it. Somebody transmitted that. I don't know who did that, but basically that command is how to transmit a tone. So if you just transmit, let's say you want to transmit a tone. There, I heard that again somewhere. You are there. Good. So what it is, the command is saying is BBTX means baseband transmission. CW means continuous wave. There, I heard one more. 8000 means 8 kilohertz. So if you want to transmit an 8 kilohertz tone, that's what you do. And 1 is 1 second long, right? Now, who wants to try out the sweep? The second one. Oh, yeah, sorry. Yeah, I heard that. So can you try, instead of 10 and 12, because it's high pitch, maybe try 8 to 10. So it will be slightly lower, but longer. So basically what that is, it will create a sweep. Yeah, there you go. It starts at the starting frequency, ends at the ending frequency, and 0.5. Yeah, I heard there somewhere. 4.5. So half a second long sweep it will create. So yeah, there. So what I'm trying to say is, while I started by using the software as software to communicate between 2 points, that is just one very, very small capability of the software. There's a whole lot of things that you can do. In fact, you can actually use this to listen to oceans, which is what I do routinely in my work. So I basically take my laptop, connect a hydrophone to it, dip it in the oceans, and keep recording. And I put on my headphones. I can actually hear how the sound of what the sound of the sea is in that band. So currently it is configured to operate in 9 to 15 kilohertz, but I can configure it to operate in higher frequency or lower frequency depending on my hardware. You can use it for ranging, you can use it for localization, you can use it for almost any acoustic work that, or acoustic devices, whatever processing that they do with this. So this is what we call a true software-defined modem, because depending on the capability of your hardware, you can just run it and it'll just work. So if you run it in a laptop without any configuration, it runs from 9 to 15 kilohertz. If you run it in that hardware, it's slightly lower frequency, you just change the frequency band, it will just work, right? And the more and more you understand, the more and more things you can do. And that's why you have a very, very long textbook of all the things that you can do in there. Now, so the last test, I don't think you will be able to do. That's just, let's say if you have a WAV file, let's say you want to play music, right? All you have to do is have a WAV file. I have one WAV file loaded in my laptop. Just use the command WAV and the file name, and it will load the file and then transmit that. It will transmit that. But there are certain things that you need to know about the WAV file. It needs to have a mono, single channel WAV file. It doesn't load 2 channels, so because it can only transmit 1 channel. And it also needs to have a sampling frequency same as your sound card. So again, in the blog, I believe there are instructions of how to do this, but I will quickly show you. Yeah, so you can see that when I do that, it loads the WAV file, and that's the data in there. And if I transmit this, sorry. Yeah, so that was a random WAV file that I could find from internet. So feel free to download any WAV files. Oh yeah, before going to the next section, so one more slide, this is what he was asking about. So a couple of things to note. While it looks very easy, like I said, this has been the result of decades of research at ARL. And if you can easily put these things in water and try transmitting, but it may or may not work. It's not, so these are some of the culprits that is causing the problem, right? The first thing is, in a pool kind of environment, not just a pool, any type of environment, is very, very reflective, especially if it's shallow. So if it's a deep, deep waters, like deep oceans of Pacific Oceans of Atlantic Ocean, it's not much of a problem. But in a pool kind of environment where you will be working on, one of the first things that you need to be mindful of is reflections. So if you are going to blast out at full power, what's going to happen is it's going to reflect off and it's going to come, and at the receiver it will receive many, many things, and then you will have collision. And this is a standard problem with wireless technologies. It's not just acoustic problem. Any wireless systems will have to have some kind of collision detection and avoidance systems. And it's especially true in the case of acoustics, because the signals that we are transmitting, you heard, it's very, very long. And the pool walls are very, very close. So the reflections and the direct arrivals come at the same time or very, very close to each other and interfere. So you need to play with your power level, how high, how loud you are transmitting. And you probably need to also play with the size of the length of the transmission, which you can, I will not go into the details now, before you get it right. Okay, that's number one. The second is propagation delay. So propagation delay may not be a bigger problem, but there is still sound travels very, very slower than light. So it still takes a time from once you transmit to get to the receiver. So do not expect instant feedback. Transmit, receive, and then, so that's something that you need to play around with to figure out how fast it is transmitting and receiving, right? The third is limited bandwidth. Again, that's, if you are trying to send images and videos, that's not going to happen. It's going to be very, very limited bandwidth, but you can send commands like what we were doing just now. Then multipath, I talked about Doppler. So Doppler is not a problem that you are seeing now because all of us are sitting and then transmitting, but when vehicles move, there is relative motion. So vehicles are moving and your transmitter is steady. So there is a speed at which there is a relative speed between the transmitter and receiver. So what that happens is the frequency that is the receiver C will be slightly different from what the transmitter is transmitted because of the relative motion. And because of that, the communication can break down. The communications that you are currently using have Doppler compensations built into it, but again, something that you need to be aware of. And time variability, again, not a big thing that you need to be aware of in the pool, but one example would be if you had calibrated your cameras on qualification day, which was an overcast, cloudy day, and yesterday you tried to use the same training set, it probably wouldn't work because it was a sunny day in the afternoon. So similar to that, the sound also changes. When you go out to sea, there are these marine creatures that are very, very active in the morning. Sometimes in the evening it's not active. So the channel actually changes. So something that works in the morning may not work later in the afternoon. So you need to be aware of it. In the pool may not be a big issue, but something there. And high noise environment. So depending on where you are operating, the noise tend to be very high as compared to terrestrial wireless channels. In the case of optical, ambient light. So if there is light as changing, the performance changes. Directionality, you need to light, the camera needs to be oriented. High absorption and optical scattering. As the distance go, you can't see the light. Okay. Now, before going into the optical side of things and RF side of things, I just want to talk a bit about the stack in UnetStack so that you understand what exactly I am doing, right? So some of you might be familiar with the concept of a network stack. So wireless communication, when I transmit or communicate from a point to point, all I am doing is transmitting from one point to the other point. So I don't have to do anything. I just transmit, the other guy receive. That's it, end of story. But if I have a third guy in the picture, just like all of us are here, I am talking, all of you are listening, that's great. But what happens if all of us start talking? None of us can make it sense of anything. So similar to that, so we need to come up with some schemes of when each of the guys are going. So either I can say, oh, one person talk one time, the second person talks next time. So it's a round robin thing. So I'm just basically dividing the time for different people to talk. So that's called TDMA. Or I can use different frequencies to talk or different languages to talk so that not everyone understands. So there are these different types of techniques that you can have for many, many different people to talk. And then when it comes to internet, I am not just talking within a room. I am trying to talk to someone on the other side of the planet. Then it has to go through many, many, many systems. So you need certain ways of figuring out how it is going and who is taking it and sending it over. And then, so to do all of this whole process, what we on land use is a technology called a network stack, basically a TCP IP stack. Many of you might be familiar with it. It's basically the backbone of internet. That's what powers the internet. And it's called a stack because many of these functions are divided into certain modules which will only take care of one thing. So a physical layer is a part of the software or hardware that only looks at what type of media that I'm using, optical, Ethernet, or Wi-Fi, and then how the signals are modulated. That's it. I don't care about how the network or other parts are used. And then there's a link layer, then there's a network layer, so on and so forth. So in the case of UnetStack, part of the function is the network stack, right? So earlier I told you at Subnoro what we do, or at ARL, part of what we do is bring the internet underwater. So if you're communicating from top side to a vehicle, that's okay. You are doing point to point. But when you use the network for many, many applications at the same time, you need the whole network stack. So for that, you can't directly take the TCP IP stack and use it there because of some of the inherent assumptions. It just breaks down. So UnetStack also has different support for different physical layers, different link layers, and different types of transport and network and other agents in there. So if currently I used an acoustic system, but what I'm doing is I want to transmit some signal or a message. It is transcoded to sound and transmitted. So if I want to transmit something through light, optical, I can transcode that to some kind of a visual element and transmit, right? Actually, that's what I want to do next. So UnetStack can also be used to convert your laptops to an optical modem. So when I say optical modem, most people think of it as LEDs, which you can build on your own. I didn't have a lot of time to do that, but I have something even better. What I have here is a bunch of QR codes, okay? So I have some of this information that I physically typed and transmitted earlier encoded into these QR codes. So ideally, if I show it to my camera, it should pick up, right? Let's see whether it does. Yeah, I think you can see what I just did. Finally. So, just to quickly recap, what I'm doing is I have my laptop running whatever you just am using. I have a camera that's looking for QR codes, and it was receiving all along. It's just that I did not print the whatever it is receiving. So I have a QR code. I'm just showing it to my camera, and then you can see it printed unit audio. Or this is a for hello SAUVC. So if I just show it, it will print it again. So that's basic acoustic comms for it. In the case of UnetStack, each of these functionalities are, or layers, are agents because UnetStack is based on a agent-based architecture called Fioge. Again, all the details on the website. So what I just did was I loaded the agent that is responsible for looking for a QR code link or an optical version of it. And then I created a socket to listen to the incoming messages. It's very similar to Linux socket programming, which calls unit sockets. And then I just typed a command, while loop where it will continuously keep on receiving whatever it sees and printing whatever it receives. So that's that. And if QR code link is, or QR link is not part of the modems that you, the software that you have downloaded currently, the reason is we wanted to show how to contribute back to the community. So if you are interested in getting the QR link, what you can do is you can go to the unit contrib repo, GitHub repo, and inside the contrib folder, you can actually see there is a QR link. You can go there, and all the documentation is there on how to do it, how to download it, how to build it, and how to put it in your soft modems and use it for an optical link. Now, I will leave, so I only have 2 more slides. I will leave you with a task, which I won't show here as the next one. In fact, this is something that you currently have in your laptops, in the software that you downloaded. If you go to the unit handbook and look for UDP link, you will see it. Basically, if you have Wi-Fi connectivity between 2 laptops, right? If both of them are connected over the same Wi-Fi network, all you have to do is there is an agent called UDP link. You just load the agent and then run this command, and that will transfer the same information over a RF link, right? And in a pool-like situation, RF may work, maybe a couple of meters, maybe that's all you need, don't know. So go ahead, download it, try it out, and the details are in unit handbook. Cool. So I've come to the end of the presentation. The aim of SAUVC has always been to be as close to real-world applications as possible. Hence, we will be introducing some tasks that might need supervised autonomy or can include underwater communication. If you use Wi-Fi or RF, it may not work very, very long range. But if you want, you potentially can use that. You can use acoustics. You can use optical. And using unit audio and UnetStack, you can turn your laptops or systems like Raspberry Pi to acoustic modems without any extra piece of hardware, just by using software. And then just make sure you have fun building all of that. And thank you.